All right, welcome everyone to 12.5. This is equations of lines and planes. As you can see, we have two parts, right? There's a part A and a part B. This is a big section. Covers a lot of stuff, and in fact, when I talk to students, right, as they're coming back and studying chapter 12 for their exams and for their finals and stuff like this, I find that a lot of students spend a lot of time in 12.5 because we'll use the things that we've already developed. We'll use points and vectors and dot products and cross products, but we use them in order to achieve something, right? We're going to be trying to achieve equations of lines and planes and when they intersect and all these sorts of things that are to come. Right? But for this video right now, for this part A section, we're just going to be talking about the lines, right? So it'll be lines and planes. Part B will be planes. So we're talking about lines right now. And in this video, we have three smaller objectives, right? I want to be able to define, oops, let's do a pen here. I want to be able to define lines in space and be able to talk about them. So we need some terminology and stuff. I want to be able to tell when lines are parallel, right? So if I give you a couple lines, kind of like an algebra question, do the lines intersect? Are they parallel? What's going on with them? And then finally, right, again, kind of parallel or intersecting, right? And it turns out there's a third option here. It'll be very interesting. We'll get into that in a little bit, but not all lines are just parallel or intersecting. There's actually a third thing that happens in space, interestingly enough, but I've said too much. So, first of all, as we're heading towards, if lines are parallel, I want to talk again about what makes vectors parallel. So V and W, what if vectors are parallel? And we actually already know something when vectors are parallel, right? The vectors are parallel when the magnitude of their cross product is equal to 0. We learned that in 12.4. However, that takes a lot to use, right? That's a long time. So in fact, there's an easier definition, right? Or way to tell if vectors are parallel, and it's if one vector is a scalar multiple of another vector. So if V is a scalar multiple of W, then yeah, they're going to be parallel, right? They're heading in the same direction. It's just they're off by a scalar, right? So this is a much faster way to tell if vectors are parallel or not. So alternatively, right, using the same idea right here, but if we break it down into their components, right, and we look at the scalar times each component sort of deal, if I solve for K, we're going to get V1 over W1 is equal to V2 over W2 is equal to V3 over W3. So they're parallel if and only if the ratios of their components are equal to each other. So if they're all equal to each other, great, they're parallel, excellent. If they're not, if one of them's different, or two of them, or whatever, right? If at least one of them's different, then the claim is they're not parallel. And we'll see how to use this here when we get to some examples. Okay, moving on. Again, we want to learn some terminology, right? So that was something about vectors. Now we're getting into the line stuff. So line terminology. The first thing, a vector equation for a line. Now we're going to specify a point that the line goes through and a direction that it's parallel to. So right, if I specified I want a line to go through this point right here. This is my point P sub 0, or P naught, right? And I want it to be parallel to this vector right here. Well then, I should be able to draw the line that goes through that point and is parallel to a specified vector. So this is maybe like vector V or something like this, right? So I can draw it. How do I find the equation for it? And so this is what this definition is all about. The vector equation is, so this is a vector equation, right? So it's a function that depends on t, but it outputs a vector here, right? So this is r with a bar over. If I had, bolding power, it'd be bold r right here. And this is equal to the vector equation, the vector that we're parallel to, times t, so this is the t, the variable here, plus r sub 0. So this is a vector that's kind of related to this point right here. And when you look at this, I want you to think about, I'll use orange, mx plus b, right? So this is a line in two dimensions, right? In the plane, we have like mx plus b. So this m is telling you something about the direction or the slope, right? This b is telling you something about the point that it's hitting. So, and then the x is like the variable. So, right, these are kind of related. They're friends here. So that's the vector equation, and that's what I want you to be thinking about when you see something like this. Okay, r is the position vector of the point P. So that's to say that r is equal to x sub 0, y sub 0, z sub 0, but now it's a position vector, not a point, right? So we can do the vector addition, we can do scalar multiplication, we can do lots of things with it, right? Okay, so that's what that R sub 0 is, or R naught is. Okay, B. T is called the parameter. So parameter, it's like the variable here, right? And then alternatively, right, there's different ways that you can talk about this. So again, if this position vector of P, R naught, is equal to X naught, Y naught, Z naught, and we know even the components of V, A, B, and C, right, then we can write a line in parametric equations, right? So we have a parameter, and we can talk about parametric equations. And this is going to be equal to, so here is our line equation right here. And this is going to be basically, if you were to just distribute this all out, we're going to have AT plus X naught, BT plus Y naught, and CT plus Z naught. There we go. So this is the parametric equations. And sometimes you talk about each one of these, right? So the claim is this right here is talking about the X things, right? It's in the first component. That's talking about X's. This one right here would be talking about Y's, right? So that's the Y component. And then this one right here is talking about Z's. And all of them depend on T, right? So that's why it's X of T, Y of T, Z of T, right? They all depend on T. And we can say that A, B, and C, right, they're telling you something about, the direction. So these are called the direction numbers of the line. So now we've defined what do lines look like in space. They are vector equations. I have one more definition for you here. This one barely gets used. In fact, I don't even plan on bringing it up at all in our notes. It's not in the web work. I don't plan on bringing it in the quiz or the exams. I'll try to keep it off the exams as best as possible. We can actually take these things, right, and we can solve each one for t if you would like. And if you do that, then you get this t is equal to x minus x naught over a. You can get t is equal to y over y naught minus over b. And you can get t is equal to z minus z naught over c. So if you take each one of these and you solve for t, that's what you're going to get. These are called symmetric equations. And it's kind of a way to get rid of the parameter here. It's another way to look at these things. Okay, that's the terminology. We know about vector equations, we know about parametric equations, and we barely know something about symmetric equations. Again, I don't really plan on bringing that one up so much. Now, let's talk about what makes lines parallel to one another. So suppose I have two different lines here, right? So I have R of t and S of t. They're parameterized both by t in this case. Then I'm going to define, first of all, the angle between them is the same as the angle between their direction vectors. So v and w. So again, this one has direction vector v. It's the thing that's next to the t right here, right? Whatever one's next to the t is the direction vector. Likewise here, w is next to the t. So v and w are the direction vectors. So if you can figure out the angle between the direction vectors, that's going to be the angle between the lines. Likewise, these two are parallel if and only if their direction vectors are parallel. So if v and w, their direction vectors are parallel. Okay, finally, like I specified at the beginning of the class, or the beginning of the video, I guess, lines that do not intersect and are not parallel are actually possible, right? And they are called skew lines. And this is something new that we don't get when we're talking about lines in a plane, right? Because all lines are either parallel or they intersect. But in space, that doesn't necessarily happen. So I have, right, if you click on this, this links to Monroe's 3D Calc Plotter. I actually have it up right here. And so you can see I have these two lines already graphed for us, right? And so right now, it looks like that they probably intersect, right? So they're not parallel to one another. But as you spin this around, you can see that, oh, actually, they're not parallel, but they don't seem to intersect. And even as you zoom out, and let's kind of increase these parameters maybe. So let's go -20 to 20 on this one. And maybe down here, oops, let me hit enter, and we will increase this one as well as we go farther and farther out. Let's do -25 to 25. Just increase even more. And again, you see that kind of the closest place that they get seems to be right around here, but at that point they don't intersect. They're off by a little bit. So they're not parallel. They don't seem to be heading in the same direction, but they don't intersect. So there's some new thing, right? And that new thing is called skew lines, right? So that is what a skew line is. That's the kind of final terminology that I want to be able to talk about here. And so the last thing, right, we want to be able to determine if they're parallel and whether or not they intersect. So I have some examples for us, finally, right? You can actually look at these things. So for each one of these cases, I'd like to determine if either they intersect. And we're going to do that. If they intersect, let's find the point of intersection. Double I, or 2, right, they don't intersect, but are parallel, right? So we should be able to determine this. And then 3, they don't intersect, and they're not parallel, right? So that means that they are skew, right? Okay, so let's talk a little bit about, right, especially we're going to see if each one, if they intersect at all. In order for lines to intersect, that means 3 things must be true. Their x's are equal, their y's are equal, and their z's are equal, right? If those 3 things are true, then they must intersect. So, okay, let's go ahead and look at 2 lines. And I'm giving them to us in different ways here. But for A, we have some nice, right, these are going to be the vector equations, right? So we have some point that it goes through, and then a direction vector next to the t. A point that it goes through, a direction vector next to the t. Oh, wait a minute here. These are 2 different parameters, right? So you need to use different parameters to see if these they intersect, because they may intersect but at different kind of times, right? Usually you think of t as like a time or something like this. So if they intersect, they may actually intersect at different times. So you want to use different parameters to not say that they have to be at the same time or anything like this. So, okay, this will make more sense as we start to solve. So again, if their x's are equal, their x's, well, actually, you kind of almost want the parametric equations here. So the x component here is going to be 3 plus, and then there's 2 t's. So that's all the x stuff. So if I want the x's here to be equal to the x's here, the x's here is going to be 1 plus negative 1s. So I'm just going to write this as negative s. Okay? So that's what it would take for the x's to be equal. If the y's are equal, we'd have 1 plus 0t. So that's just going to be 0. And then if the y's are equal here, we'd have negative 2 plus 3s. And I'm sorry, sometimes my s's look like 5s. I'm going to try to do a especially good job, but here comes a 5, right, in just a second. So please make sure you're differentiating maybe on your paper and stuff, and I'll try to do a good job here between s's and 5s. Okay, 0 plus 1t, so it's going to be just t, is equal to 5, there we go, minus 2s. Okay, so if they intersect, we need these 3 things to be true, right? And so in fact, let me see here, which one do I want to start with? Well, actually, maybe this first one right here. Sorry, I was just thinking here for a second. This one seems nifty, right? Because there's no t's, right? So if I was to take this one and to solve, right? Again, I want all 3 of these to be true. Solve it for s. I would have 3 is equal to 3s. So my only hope is if s is equal to 1, right? So I need s to be equal to 1. If s is equal to 1, maybe I can use that down here, right? So I have t is equal to 5 minus 2s. So 2 times 1, that would be 2. So 5 minus 2 is 3. So t would be equal to 3. So if I have any hope of these things being equal, according to the second equation, s needs to be 1. According to the third equation, t needs to be equal to 3. Let's see if it works out. So if I plug it in up here, so 3 plus 2 times t needs to be 3. So 3 plus 6, I would have 9 is equal to, and if I plug in s equals 1, I have 1 minus 1, 0. No. So do they intersect? No, they do not intersect. Okay, so that takes care of this first one. They intersect. No, they don't. So we're in either 2 or 3. They don't intersect and are parallel, or they don't intersect and are skew. And so we're going to use this idea with direction vectors, right? So they're direction vectors. We're trying to figure out, are they parallel or not? So the direction vector 2, 0, 1, that's the direction vector for the first line. The direction vector for the second line is, let's see, -1, 3, -2. And the question is, are they scalar multiples of one another? Can you find some scalar, k, so that if you multiply something by -1, you would get 2. Something by 3 and get 0. Something by -2 and get 1. And the answer is no, right? So if you take k times -1 and you want to get out 2, that means that your only hope is if k is equal to -2. If you would like to take something times 3 and get 0, now I'm looking at the second components, right? Second components. Something times 3 is equal to 0. Well, the only way that you're going to have that happen is if k equals 0. But k is a scalar, right? It can't be equal to both of these things. So, not parallel. So, equivalently, right, we know about this thing right here, right? If we took the ratios, we should see that they are not equal to each other. So this is kind of more using this one up here, but let's also use this one really quick to just verify that this also works. This would be like if I was solving for k, right? So, okay, if I was to solve for k, let me use maybe green here, I would have 2 divided by -1 needs to be equal to 0 divided by 3, which needs to be equal to 1 divided by -2. Are all of these equal? Well, this one's equal to -2, this one's equal to 0, this one's equal to -1/2. No, they're not equal. So, this is another way to say that they're not parallel. Right? As we saw, the first one we'd say k needs to equal -2, second one k needs to equal to 0, and in fact this one quickly shows that the third one says that k would need to equal -1/2. But no, these aren't equal, so they're not parallel. Okay, so which one are we in? We are in case 3. They don't intersect, and they're not parallel. So case 3. I'll use the big Roman numerals here. Why not? Okay, B. Let's try another one here. 2 different lines. They're not the same as up above here. Notice I had a typo, so I fixed this on mine. Of course, when you print out your notes, it'll already be fixed. It'll be a 9 there. I don't know what I had. Maybe an 8 or something. I just fat-fingered it and messed up. But anyway, I have it corrected now. So, okay, same as before. Let's figure out, do they intersect or not? Well, if they intersect, we need the x's equal. And notice now I've given you the parametric stuff. So x is equal to the x here, 3 minus s. I need 9 minus 5t should be equal to 3 plus 5s. And I need t equal to 2s. So I need the x's equal, I need the y's equal, I need the z's equal. That's the way that it happens. So, okay. Notice, kind of for all these, it's solving systems of equations. So I like the substitution whenever possible. I'm going to go ahead and take this and substitute it into the first one, just because this one's relatively nice, this one's okay. So let's see what that says. So if I take that and I substitute it up here, I'm going to have 1 plus 2 times t. But instead of t, let me do 2s. So 2 times 2s, so it's going to be 4s, is equal to 3 minus s. So I can go ahead and solve that now, and that says that 5s is equal to 2, which means that s has to be equal to 2/5. Okay? So s has to be equal to 2/5. This one right here says, well, if s is equal to 2/5, then t has to equal 4/5. Okay, so I now know what my s and my t are. That's what makes the x's and the z's equal. So the question is, well, what about for this third one right here? Okay, so if I plug in t, 4/5, I get 9 minus, the other one, 5t. 5t. Is that equal to 3 plus 5s? S is 2/5. All right, so on this left-hand side, let's see. I need a little bit more space here. 9 minus, the 5's cancel here, and I'd have 9 minus 4. Is that equal to 3 plus the 5's cancel here, and I get 2. So this is 5 is equal to 5. So yeah, actually they do intersect. Yes, they intersect. And so, for these three cases that I have, we are in case 1. Case 1. Okay, and then finally, third example here, another way that you sometimes see lines. So this is L1 is specified by these parametric equations, right? So this is the x values, the y values, the z values, and line 2. Oops, and you can see I made a mistake. So x of s, y of s, z of s. And again, another little mistake here. I'll fix this in yours. That's okay. Okay, so what happens about these? So first of all, do they intersect? Well, actually, we can look very quickly at the z's. Z's, we have 4 would need to be equal to -9. So no, they don't intersect. Because there's no way that you could ever have 4 equaling -9. Okay, so we are in either case 1 or 2. As you can probably guess, we're going to be in case 2. I've already done a 3 and a 1. It's going to be case 2. But let's verify this, right? I want to show you that case 2, they're in fact, they don't intersect, but they're parallel to each other. So, okay, just as before, right, in the first case, of course in the second case, or in part B here, we already saw that they intersect, so we were done. But let's go ahead and now look at their direction vectors. So the direction vectors, for the first one here, it's 1, -2, 0. So it's the thing that's next to the variable, the thing that's next to t in this case, right? There's a 1 here, -2 here, and this is technically plus 0 t, if you'd like. So that's the direction vector. And it needs to be some scalar multiple of the direction vector of the other one. So the thing next to the variable. So -2, here 4, and the variable's s here, but there's nothing here, right? So 0s, if you'd like. And so, can you find some scalar that multiplies by -2, 4, and 0, and gives out 1, -2, and 0 correspondingly? And the answer is yes, that these will be parallel. In fact, it'll be k equals -1/2. So let's go ahead and double check. So if k equals -1/2, 4, 0, then we can go at -1/2 times -2 would be +1. -1/2 times +4 would be -2. -1/2 times 0 is going to be 0. So yes, we can find a scalar. They are scalar multiples of one another, right? Let's show using the other way, right? So if I was to solve for k, I would have 1 divided by -2, -2 divided by 4, right? We're just taking ratios here. And this one's a little bit stranger, 0 divided by 0. That doesn't really work when you have the zeros here, as you see. But yeah, so this is -1/2. This one's -2/4, which is the same thing as -1/2. And this is 0 over 0. Kind of exclude this one. So yes, they are parallel to one another. So we are in case 2. Parallel. Okay, and that is it for now. Like I said, this is a big section. We're going to be doing some exciting things in class. Really, really should not miss it. I'll see you next time when we talk about, well, in class, more lines. In the next video, more planes. See you then.